Welcome back. I'm Janka and this is Biomedical Signal Processing, Lecture 7, and this is the second chapter of this lecture. So we have seen in the previous chapter that when we are getting longer and longer windows, you have better and better resolution in frequency, and vice versa. When you have shorter time windows, you have a better resolution in time, but you have a very bad resolution in frequency. This is the so-called time frequency uncertainty. Let's see what is happening here. Why is this so? In the very simple case, you are using a rectangular window in the time domain. So when you are getting that short segment, you are just using this rectangular window and you are calculating the spectrum over that short segment. As we have already learned about it, in the frequency domain, it will mean a convolution with a sinc function. And as we have seen it in the previous lecture, it means that your resolution of the spectrum will be defined by the width of this lobe here, of this sinc function over here. It's very easy to calculate what is the correspondence between the two. So if you have a rectangular window with delta t width, then what is the width of this side lobe of this sinc function? What is the resolution of your spectrum? So if you have this rectangular window, you have its Fourier transform as a sinc function, and as the width, we have said that this is the full width at half maximum, which is where this sinc function is reaching from value 1 to 0.5, so it's half in amplitude. And this means we are looking for that sinc value on this x-axis, which will give us a 0.5 value on the y-axis. So what is that number of which the sinc function gives 0.5? If I say that delta t, so the height here is 1. It will mean that you have this drop at 0.603, and this will be the value of this resolution. And if you are multiplying the two together to get the time uncertainty, the time resolution and the frequency resolution in one number, in this case we are multiplying these two resolution numbers with each other, you will get this 0.603. So this is a number which is expressing the uncertainty of simultaneous frequency and time resolution. And we will see whether we can get a lower number or not. If I go on, the next possibility is a Gaussian window. It will be a lot better because the frequency, the Fourier transform of a Gaussian window is a Gaussian window. So here you can see the original function, and here you can see how its Fourier transform is changing. So it has some different scaling and some different number in the exponential, but it is a Gaussian function. And then we can calculate this delta t and delta f accordingly. So again, where this Gaussian window is reaching from 1 to 0.5, there you have the full width at half maximum value. And then you will have a number for delta t and one for delta f. So these are the two resolution numbers you have to count with. And then if you are multiplying these two numbers together, then you will have this 0.4412 as your uncertainty. So if you remember, we had 0.603 with the rectangular window, and we have this lower number, 0.4412, with the Gaussian window. So you can have a better uncertainty with a Gaussian window than with a rectangular window. What does it mean? That if you are using a Gaussian window when you are doing the short time Fourier transform, then you will have better resolutions than with a simple rectangular window. Here is, this slide is showing you what if instead of delta t And delta F, you are using the deviation of these Gaussian windows because sometimes it's easier to calculate with, and you will have the same methodology for calculating the full width and half maximum, and you will have this number 1/4p squared. So this will be the uncertainty, which is very similar to the previous number, just in deviation. That will be the only difference. So this is the so-called time frequency uncertainty principle. It means that the product of the variance for time and frequency is never smaller than this value, which is the most standard with the last deviation values, which is this 1/4 square p number. So it means, and actually this is your best option, the Gaussian function. So there is, to our knowledge, no better solution than the Gaussian function if you would like to have this maximal resolution in time and frequency simultaneously. So the Gaussian function will give us this, and the so-called Gabor function. They are very similar to each other. We will just see how similar they are, and they can do the same thing for us. So they can give us good resolutions for spectrograms. This was the second chapter of lecture 7. We have learned about time frequency uncertainty. And to get to the next chapter, please take the quiz below. Thank you.